Hello, my name is Minji Yun, and I'm a junior at Marion High School. I was working on an aspect of Pico dark matter experiment. Before I go into what my project was, I will be talking about what dark matter is and how they were detected before. So, dark matter takes up about 85% of the universe's mass, and it was originally detected by its own gravitational effects on ordinary matters. And so far, the scientists have never observed individual particles of dark matter. And Pico was trying to do this by using bubble chamber. A bubble chamber uses superheated liquid inside, which is metastable state. So when a particle hits an atom inside, the atom will be ionized and it will cause heat, which will cause a mini explosion inside the liquid. When this happens, the liquid will go into phase transition, which means it will turn into gas and produce bubbles. And Pico was able to see and hear the bubbles by using cameras and acoustic transducers. So what acoustic transducers do is that they collect sound energy and convert it into another form of energy. And they also allow event-by-event background discrimination. So if you look at the graph here on the left, the red line represents the noises of radioactive background particles, and the black line represents the noises of dark matter particles. Well, neutrons, but neutrons work the same as the dark matter particles. And if it's in the right side, it means they are louder than the ones on the left side. So it is obvious that the dark matter particles have smaller noises, less louder noises than the ones that are radioactive. And the problem is Pico wanted a high sensitive transducer so that they can collect more data from dark matter particles noises, but the transducers that they were using had piezoelectrical material inside. And that material is made out of ceramics, which means they are radioactive too. So they wanted to increase the sensitivity of the transducers without using any more amount of ceramics inside. So my project was focusing on the hypothesis where the transducers with larger Faraday enclosure sizes will have more sensitivity than the ones with smaller sizes. So these are the four different sizes of transducers that I made, and I kept the same amount of ceramics inside. So the only different thing would be their sizes. And I exposed them into the same white noise by using air spray test system right here. Also, before I went into testing all four sizes of my transducers, I picked a single transducer and tested it 5 times by repeating the process. And this is a power spectrum versus frequency graph of my results. So as you can see here, the lines are pretty much identical, which means I was using the same technique all the time, and the sound that I was exposing the transducers into was consistent all the time. So and then I moved on to testing my transducers, 4 sizes of transducers. So the blue one is the smallest transducer, red one is the third biggest transducer, yellow one is the second biggest transducer, and purple one is the biggest transducers that I made. And in general, the biggest transducer had more sensitivity than the smallest one right here. And the graph is in logarithmic scale, so that means the small gap here in this graph is a large difference outside of the graph. Also, they were all inside of the limit of Pico dark matter experiment, which would be 200 kilohertz. Also, they were significantly more sensitive on 90 to 160 kilohertz right here, and 0 to 30 kilohertz right here. And you can see that the graphs are in scales too. So this results supported my hypothesis, which was transducers with larger Faraday enclosures will have more sensitivity than the ones with smaller enclosure sizes. Thank you for listening.